principle, just like the atoms we had before. Now we're going to use something which we call the zigzag. Well, I didn't want to call this a zigzag. This is all unit segments. So you have 90-degree turn, 90-degree turn, 90-degree turn, 90-degree turn, no straights. This turns out to be universal in a strong sense. It can fold into anything. And so we can use it to connect these parts together. So what we're going to do is have the A1 gadget. Then we're going to have a whole bunch of zigzags. You can go wherever you need to go. Then we'll have the A2 gadget, and then we'll have the universal zigzag gadget for a long length of it. And then the A3, and then alternating between zigzag and the AI. And at the end, we'll have enough zigzag that we can fill all this sort of extra garbage space. But we will use this garbage space in order to route around. So maybe A1's going to go here, and so we do this thing. It's a kind of cooker. We go back and forth like that. Then we'll have the zigzag and say, okay, I want to go over here next, and then we'll do A2 there, and then we'll route over here. And because this is in 3D, crossings are not an issue. I can just go out into the third dimension. We don't need much of a third dimension. 8 is enough. You can just enough to go over each other. Okay, and then at the end, we're going to fill in all the space with the zigzag. So let's talk about the zigzag. What we claim is a couple of different senses in which it's universal, but the key idea is these sets of gadgets. So we're drawing here a 2x2x2 cube made up out of 8 little cubes. And if you look at what we've drawn here is the elastic that goes through the centers of the cubes. And notice it turns 90 degrees at every voxel, at every little cube. So this is part of, these are zigzag constructions. So what we want to say is that if you sort of, one sense of universality is that the zigzag structure can fold into any polycube structure. Polycube is the 3D generalization of polyominoes that we saw last time, from polyomino packing. That's not true. But if you take any polycube structure and you just scale it by a factor of 2, so you place every cube with a 2x2x2 grid, like this picture, then it's still not true, but it's better. So what's true at that point is if you take any path of 2x2x2 cubes, this is what we would call a Hamiltonian shape, because there's one path that visits everything with no collisions. So it has to be a path that does not hit itself in 3D. Then you can follow these gadgets in order to make any turns you need to do. Or you can go straight. Everything is possible. I will talk a little bit more about that in a moment. So 2x2x2 refinement, meaning scaling everything by a factor of 2, allows the zigzag to make any Hamiltonian shape. Scaled by 2. But that's Hamiltonian shapes. Now, conveniently, there's this theorem which is used a lot in computational geometry, and we use it in this hardness proof, that if you take any shape and you refine it by 2x2x2, or scale by a factor of 2, then it becomes Hamiltonian by a similar kind of gadget construction, although it's easier. If you just want Hamiltonian paths, you don't care about where you're turning and where you're not turning. So that's a pretty easy proof. Left as an exercise to you, and sort of an aside from this issue. So we take any shape, we 2x2x2 refine it, we make it Hamiltonian, then we 2x2 refine it again, in total 4x4x4 refinement, and then zigzag path can make that polycube shape. This is for any polycube. So that's cool. Now, I'll mention here in this proof, one of the issues, which we'll see a bunch of times, I'm just going to mention it here, is we have a parity issue because the cubical grid is too colorable. Right? You can checkerboard the 3D grid on squares. And so what that means is every time you go from one cube on the grid to another cube on the grid, you're switching parity. So if you checkerboard the 3D space, black and white, it was going from white to black, then black to white, then black to white, then alternating black and white. And easier to do than to say. And so that's a constraint. So for example, it is impossible to, in a 2x2x2 thing, to, let's see, enter from this cube, the front cube, and exit from this one, just by counting argument. So you start, let's say this is a black cube, this one's also a black cube, and so you start black, and then you alternate black, white, and there's 8 things to visit. You want to end black, that's not possible. You have to end white. So if you enter on a black cube, you will leave on a white cube, and if you enter on a white cube, you leave on a black cube. So that's a constraint. Doesn't really get in the way here, but it's something you have to keep track of, and the theorem wouldn't be... What you'd like to say is, well, I can enter from any cube and leave from any cube. And you could actually prove that by induction, except the basic